dear learners. In this class, we will try to understand more important features about airglow emissions, and subsequently we will see what is space weather, and we will learn a lot of information about space weather. So, in the last lecture, we have seen what are the auroral emissions, and airglow being a very closely related phenomena is quite different in the sense of its source mechanism or features or brightness, many other things. So, we have seen the contrast between the airglow and auroral emissions. In this lecture, we will see more aspects about the airglow emission. So, just to maintain some continuity, this is how the airglow emissions will look like, which is a constant or uniform background in the sky. This background appears to be in the green color, which is primarily because of the radiating species, which is oxygen in this case. And then this is a photograph taken at the polar locations showing the intense auroral emissions in the North Pole. So, from this picture itself, you can clearly understand that the auroral emissions are highly structured, whereas the airglow emission is a uniform and faint luminescence in the sky. Airglow emissions are global, they can be found anywhere. Auroral emissions are particularly local to the polar skies. And the sightings of the auroral emissions pretty much depend on the solar wind conditions, or more importantly, the eruptive phenomena on the sun. So, the primary connection being the plasma outburst or the huge bubbles of plasma, magnetized plasma reaching the upper parts of the atmosphere through the mesosphere. So, for the auroral emissions, an interaction between magnetosphere, ionosphere and thermosphere must happen under favorable conditions of interplanetary magnetic field. But auroral emissions are also very intense, and at the same time airglow emissions are basically due to the electromagnetic radiation that we receive from the sun. Now, we have already seen what is magnetosphere, what are different regions and sub-regions of magnetosphere. So, having some knowledge about the auroral and airglow emissions will help us appreciate what is space weather and understand various aspects about space weather, which we are going to discuss further ahead in the class. All right. So, types of airglow depends basically on the time of observation. So, generally like 42 to 45% of the earth on any given day, any time, at any given time, earth is in the day side, there is direct sunlight, and 33 to 35% of the earth is night, there is no direct sunlight, and 20 to 25% of the earth is twilight, which are basically the I am referring to the dawn and dusk periods of the day. Dawn and dusk. Right. Now, this twilight glow, during this the sun is not directly visible or sun is below the horizon, and if you rise in altitude, you will be able to spot the sun sitting below the horizon in the frame of reference of the earth, of course. Now, most importantly, there is, since the airglow emission is directly related to the electromagnetic radiation or light that we get from the sun. So, electromagnetic radiation is directly responsible for the formation of airglow. But so, we should also ask why there should be twilight glow or why there should be night glow. The reason for that is basically the chemiluminescence reactions, in which a particular chemical reaction in the absence of sun can also excite atoms and molecules. Their subsequent de-excitations will produce the twilight glow. So, the source mechanisms for these three emissions are distinctly different. If you look in detail, the most important source for the production of airglow is oxygen and nitrogen. Why? These are the most abundant gases in the Earth's atmosphere. So, naturally, these emissions will be produced by these gas species. So, these species participate in a variety of chemical and processes that are initiated directly or indirectly by the solar radiation itself. The solar UV photons are mainly responsible in initiating these reactions, leading to the formation of airglow or leading to the emission of light, primarily in the green and red parts of the visible spectrum. That's right. This is the most important information pertaining to air glow. So, it is not just oxygen and nitrogen which emit air glow. There are several other species like hydrogen, helium, nitrogen, N plus O, O plus OH. All these, the transition, the type of transition is basically electronic transition as far as it is atoms, and some molecules also emit air glow due to the electronic and vibrational excitations and de-excitations. Their characteristic wavelength at which these species radiate light are these wavelengths, in nanometers, and altitudes at the typical altitude at which these emissions can be found are these. So, for example, hydrogen can emit at 656.3, almost at the beginning of or at the edges of the red part of the visible light, at altitudes 100 to 2000 kilometers. So, it can vary anywhere. So, we already know the uppermost part of the Earth's atmosphere is primarily dominated by these lighter species, and helium can radiate between these two altitudes, which is a wide range, by the way. Nitrogen can radiate between 130 to 300 kilometers, and depending on, if we look at the energy level diagram, we will be able to understand how many different transitions can lead towards the air glow. And N plus, of course, and most important is the oxygen emission, which is emitted at 557.7 nanometers, 630 nanometers, 844.6 nanometers. And these three emissions are the most readily observed air glow emissions. So, every atom, depending on the availability of incident photons or excitations, will emit its characteristic wavelength, which means that by looking at the emission or its wavelength, we can be able to guess which particular species is emitting that radiation, emitting that visible light, and at the same time, each of these excitations and de-excitation processes depends on the temperature, depends on the ambient densities, so many other things which are characteristic features of the emitting region. So, depending on the light that we get, we can infer a lot of information about the physical or chemical state of the emission region. So, in that sense, oxygen air glow emission is a very important tool, very important spectroscopic tool, which can help us gaining valuable insights into the upper atmospheric state, structure and dynamics. Okay. So, in addition to this hydroxyl molecule is also a very important emitting species which emits at this wavelength and primarily in the 70 to 100 kilometers altitude region. Now, these are air glow emissions, right. So, the same spectral transitions can also be initiated by energy in the form of particles, right. So, when that happens, because of the immense amount of energy that is available with the plasma, the strength of these emissions or the intensity of these emissions will be very large in comparison to the air glow emission intensities. The strength will be of the order of several kilo Rayleigh or thousands of Rayleigh, whereas in the case of air glow emissions, the strength is typically few hundreds to 1000 Rayleigh, right. So, that is what you see here. Oxygen air glow can go up to 0.270 kilo Rayleigh, and whereas the same emission, the same spectral transition can produce up to 100 Rayleigh in the case of auroral emissions. So, here you should remember that 1 Rayleigh is equal to 10 to the power of 6 photons in units. Okay. So, because of this, auroral emissions, of course, are primary markers of the interaction of solar energy with the Earth, with the Earth's upper atmosphere, right. But they are not a daily or not, they are not a global phenomena. So, the purpose of this table is to understand many species can emit air glow emissions, and the characteristic wavelengths span the entire electromagnetic spectrum, primarily in the visible range. Let us say, for example, the hydroxyl molecule can exhibit air glow at this wavelength, which is pretty much invisible or which is infrared radiation, right. So, you need to have that particular sensor to be able to detect this air glow emission, right. So, air glow is important in the sense it can provide highly valuable information about the atmosphere, and many species can radiate airglow, and it is very important for you to remember the type of spectral transition and also the characteristic wavelength at which these emissions are made, and a comparative picture between airglow intensity and the auroral intensity. Now we talk about in this lecture we will talk about two important airglow emissions which are the most readily observed airglow emissions in the upper atmosphere. So first one is uh, 557.7 nanometer green line dayglow emission. So this is the wavelength that we are talking about at which we see the light to be emitted, and we call it as the green line because the color in which this wavelength appears will be green. Okay. So green line dayglow emission is by far the most readily observed airglow emission and the brightest airglow emission in the atmosphere. So now you just have to understand that this is a light. This is the light that we can see. Okay, where do we see this? We can see in the upper atmosphere. So if you can see some images which are grabbed by the International Space Station, you can be able to see in many of those images there is a hue of green and red colors appearing in the upper part of the sky. Okay, so these two emissions are basically the airglow emissions that I am talking about. So many times NASA releases from time to time images taken by International Space Station. They are available widely over the internet. You can see them and get a feeling of these airglow emissions that I am talking about. And these some of these images may also contain sightings of aurora over the North Pole or the South Pole. You can browse the internet and get a feeling for these visible features, and then you can connect what I am talking about, what the physics that I am talking about, how these things actually work, things like that. Right. Now, this emission, like I said, is basically due to the excitations and de-excitations in electronic excited states. So we should actually be knowing which spectral transition is responsible for the emission of light at this wavelength by oxygen. So of course, it is oxygen which is emitting this light. The spectral transition is singlet S to singlet D. This is the spectral transition which results in the formation of green line airglow emission. Now, if you look at the energy level diagram of ground state of oxygen, you will be able to see that the ground state is triplet P012, and immediately above we have singlet D and singlet S. So when I am referring to this particular spectral transition, which depends on a lot of things, on the availability of excited state or on the population of this excited state, how much it gets populated, and subsequently when this lifetime is exceeded, a spontaneous emission will happen, which will result in the emission of this wavelength. So as a result of this, so many other emissions are there, many other spectral transitions are clearly visible within this figure itself. Right. We are not going to talk about all of them, but the point is this spectral transition results in the formation of airglow. Right. Now, oxygen is available everywhere in the atmosphere. It has a profile, of course. Its density or the number of oxygen atoms that you can find in the atmosphere varies with respect to height. And at certain point, the molecules being dissociated by the incoming solar radiation will create a lot of atomic oxygen population at 150 or 100 kilometers altitude. But more importantly, the variation in the density of oxygen atom tells you that the available number of oxygen atoms is not same everywhere. So generally in atmospheric and space physics, we always try to ask how things are changing vertically upwards. So if I take the temperature for the simplest example, I know that temperature initially decreases with respect to height, increases and then decreases and then increases. Right. So the point is, if we take the number density of, let's say, neutral number density, we know that the number of atoms or molecules will decrease exponentially upwards. So with this decreasing exponential with this exponentially decreasing edit here. So with this exponentially decreasing number density, because the amount of photons that you get at this wavelength primarily depend on the number of oxygen atoms which are there, right? So using some remote sensing experiments, the variation in the number of photons emitted at this characteristic wavelength as a function of height has been retrieved, and it looks something like this. So what does it mean? This means on the x-axis you have the what you call as the 5577 angstrom volume emission rate, we call as VER, which is basically the number of photons per centimeter cube per second. Number of photons that can be seen per centimeter cube in a unit volume per second, right? So this will increase starting from a very low altitude of 75 kilometers. The number of photons will increase. That means there are more oxygen atoms here which are radiating this particular emission. It will increase and it will decrease, and then it has a shape like this, right? So this means that at these altitudes, the intensity of oxygen air glow will be like this. You have a region nearly the upper mesospheric region where the number of photons will be maximum, and then the lower thermospheric region where the number of photons will again be maximum. Now, most importantly, it's not a direct transition. It's not always. So, if you look at this energy level diagram, you will realize that many transitions are going on simultaneously, and it's not necessary that every time oxygen is excited, you will only get the green line air glow emission, right? So that means that the way in which oxygen atom is excited, the ambient temperature, the population density, everything will decide subsequently how many photons are emitted. Of course, it is directly proportional to the number of oxygen atoms which are present, right? But the point is, the way this curve is looking tells you that the number of the intensity of air glow emission is not constant throughout the atmosphere. Or we can also infer one more very valid information is that at different heights, the way in which oxygen atom is excited into this singlet S state are different. So there are certain processes, chemical processes which are going on here, which will populate oxygen atom into singlet S, and there are entirely different chemical processes which are happening in the lower part of this peak, which will populate oxygen in the singlet S state. So because of all this, the profile, the volume emission rate profile looks something like this. So the meaning of this is that if you have a sensor, if you have a detector which can tell you how many number of photons are present at any given altitude. So, and if you keep flying this equipment vertically into the sky and you plot the counts at different heights, this is what you are going to get. This is the meaning of this curve. Right. Now, without going into many details about the photochemistry is basically chemistry induced by the photons or incoming electromagnetic radiation. So, without going into the details, we will briefly touch upon some aspects of this green line air glow emission. So, the sources of production of oxygen in the singlet S state in the mesosphere, so which I am referring to this peak. Okay. So, the primary source of production is the photodissociation of molecular oxygen by solar extreme ultraviolet radiation photons, which is basically 10 to 100 nanometers. So, sources of production, what do I mean? Sources of production. So, these reactions will make sure that oxygen is populated into this singlet S state. So, first one is photodissociation, in which Hν, the electromagnetic radiation within a threshold wavelength, is dissociating these oxygen molecules into two atoms, out of which one is in the excited state. The other very important source of production for the oxygen airglow emission in the mesosphere is the three-body recombination reaction, in which triplet P, if you go back to the energy level diagram, this is the state that I am talking about. The triplet P state, in the presence of a third body, or which is just a platform for this reaction to happen, that's why we call it as a three-body recombination reaction, will recombine to produce molecular oxygen in the excited state. The third body is not participating directly in the chemical reaction. And then here, this excited molecule will again collide or interact with a ground state oxygen and produce neutral oxygen, of course. And then conserve this, you will find out that the one more oxygen atom is now in the excited state singlet S, which is actually what we need, because if once we populate oxygen into this state, subsequent de-excitation will only give you 557.7 nanometer emission. So, it is natural that we are looking at only those processes which are guaranteeing the oxygen airglow, or which are guaranteeing the oxygen being excited into singlet S. Right. Now, the rate at which this reaction proceeds depends on a lot of things, depends on the reaction rate coefficients, which in turn will depend on the temperature. Right. So, that means the ambient conditions, it is not sufficient for you to just have photons and oxygen atoms. The ambient conditions heavily depend on the temperature. For example, if there are two competing processes, the reaction rate coefficient of a certain process is very, very high. So, what will happen? The rate at which this reaction will proceed will be very, very fast. So, if given enough number of atoms and molecules which are required to be the reactants of this process, if you supply enough number of that, then this reaction will make sure it will consume the entire population that is available in that particular volume. But of course, if you have two processes which are competing with each other, both of these processes will compete to consume the available species which are there, right? So, that means that these are only the major reactions that I have highlighted here. There are many other processes. You can refer to any standard book, or even on the internet, these things are pretty much available, right? Now, most importantly, these are the production processes, sources of production. I mean, how many number of atoms, oxygen atoms, are populated into this state is what is being shown here. Now, loss processes refer to all those chemical reactions in which this singlet S will not, the de-excitation will not happen into the singlet D, because singlet D, if the transition happens into singlet D, you will get a green line airglow emission or that particular photon, right? But if it is not required that the transition will only happen to that, you have a look at the energy level diagram, you will realize yourself that it is not necessary that way. So, loss processes refer to all those chemical reactions in which the populated excited state may be lost without producing the targeted photon or the intended photon. So, the loss processes include a lot of let us say interactions with molecular oxygen, or many other states of molecular oxygen, all of which are not producing. See, you see that this transition is directly going into triplet P, which is actually the ground state, right? So, these processes, so now if you have equal number of this to this, then there is no chance of getting a photon, because this has to go to O singlet D. Only then you will get 557.7 nanometer emission. But it is not true. These two, all the loss processes put together, will not be able to consume the entire population in the excited state of oxygen, which means there is significant population going towards the singlet D and producing the green line photon, right? Some simple mathematical formula in which you can find out the rate at which, the production rate at which photo dissociation of O2 is happening, which means the source reaction is happening. And there are some parameters on the right hand side which indicate what is the quantum yield of the reaction and what is the photo absorption cross section, how effectively a photon can be captured for the dissociation of oxygen. And this reaction the photo dissociation of molecular oxygen heavily depends on the solar zenith angle. The solar zenith angle is basically an angle if you are looking at the sun, if the sun is at this place, or if this is the normal and if the sun is here, for example, this angle is the solar zenith angle. So, solar zenith angle will be 90 in the morning and in the evening, and will be 0 in the afternoon. Right. So, solar zenith angle decides how much amount of photons are available. So, what happens is when the radiation is traveling vertically downwards, it will encounter the atmospheric column, and the attenuation will depend on the length on the length it travels. So, as the radiation is traveling into a thicker atmosphere, the attenuation will happen, and if it is adopting a slanted height, the maximum amount of attenuation will happen at a particular height, and if the radiation is falling in a normal way, the maximum attenuation will happen at a certain different heights. Right. So, the point is the amount of photo dissociation that can happen in the atmospheric column heavily depends on the solar zenith angle. Right. So, this is a simple formula. So, this is the production that I am talking about. Quenching refers to all the loss processes, which could be because of this chemical reactions that I have highlighted here. So, if I combine these two things, so the total production or total yield in 557.7 nanometers will depend on the rate at which photodissociation is producing oxygen in the excited state, and also at the same time how much of the population loss processes are able to take away. Right. So, this is how we combine these two things, and we write an effective expression for calculating the volume emission rate of oxygen in the singlet S state. So, similar to the green line emission, another important Airglow feature is the red line dayglow emission, which happens at 630 nanometers. So, earlier it was 557.7 nanometers. So, if you want to do any research in atmospheric and space physics, this emission you will come across many number of times, because this happens to be a very important tracer for understanding the solar forcing on the upper atmosphere. So, the second important emission is red line Airglow emission, which happens to 630, which is sitting in the red part of the spectrum. Right. So, the peak emission is between 200 to 250 kilometers. So, this is where it will be found, 200 to 250 kilometers, 200, yeah, 200 should be fine. This is where the emission is found. Earlier, you have an emission which is appearing at two different altitudes, one lower thermosphere and upper mesosphere. It's not here, it's not like that, it's just a thermospheric emission, which is the intensity could be on this, the intensity could be depending on the time, of course, it depends, and depending on the several conditions. So, the intensity is comparable to the intensity of the green line emission. So, this is the most readily observed atomic oxygen green line emission, and the transition, just like I have explained the transition in the last slide, the transition that is responsible for producing this emission is singlet D to triplet P. Go back to the energy level diagram. So, the 630 nanometers emission is this that I am talking about. This is the green line emission, this is the red line emission, and the energy difference is 1.96 electron volts to 0.00 electron volts. Right. So, the total angular momentum is 0. Of course, this you should be able to generate these energy level diagrams for any atom. Okay. Now, again we talk about the source and sink processes for this Airglow emission. Source processes are those, in this case, the chemical reactions or photochemical reactions which will put oxygen in the singlet D state. What are those? The first and very important process is the photoelectron impact, in which a photoelectron is colliding with triplet P, which is the ground state, and producing a singlet D. The same photoelectron is emitted out. So, that means you have an oxygen atom in the excited state, which subsequently may produce the red line emission. And this process is the dissociative recombination reaction, in which an oxygen molecule, when interacts or when collides with a thermal electron, can this oxygen molecule being ionized will be dissociated into two oxygen atoms, one of which is existing in the singlet D state, the other in the ground state. So, all of these on the right hand side you are able to see the singlet D states or oxygen in singlet D. Right. The third one is nitrogen interacting or with O2 producing singlet D, and photodissociation of directly with molecular oxygen can also produce singlet D. And the radiative transfer, if you go back to this energy level diagram, all the photons, all the de-excitations from singlet S to singlet D are of course producing this emission, but at the same time they are populating this state which is necessary for a transition at 630 nanometers. Right. So, this reaction is actually a source for the 630 nanometer emission. So, similar to this, we also have the loss mechanisms or loss processes, which take care of the which remove some of the population of oxygen in the excited state, and it could be interaction with nitrogen, oxygen, or any other processes. So, we can combine the both the production and loss processes, and we will be able to get an expression, a simple expression which will tell you how many number of photons can be expected given the concentration of oxygen is this, given the concentration of nitrogen is this, given the intensity is this, given the solar zenith angle is this, etc. That actually becomes a calculation if you have to do some, if you want to actually know, or if you have a measured profile and you want to match this. So, this type of calculations can tell you what is going on in the upper atmosphere. So, we have learned about airglow emissions, how they are produced, and two important airglow emissions like which are emitted by oxygen in particular, 557.7 nanometers and 630 nanometers, and their usefulness in probing the upper atmosphere in a remote way. And if you look at this picture, this is a photograph taken from the International Space Station, where you can clearly see the green line and red line airglows present as a uniform background covering the limb of the Earth. Right. So, in the subsequent lectures, we will try to understand how these very emissions can be very important tracers for monitoring the space weather activity, etc. Yes. So, in this lecture, we have understood the importance of airglow emissions and the production mechanism of airglow emissions, and we have looked in detail about two important airglow emissions emitted by oxygen, which appear green and red in color at 557.7 nanometers and 630 nanometers. In the subsequent lectures, we will learn more details about airglow and how it can be useful to probe the upper atmosphere.